Hello, my statters. Well, earlier in the lessons, we talked about, or I said that there was going to be another concept, which is going to be an awful lot like mutually exclusive, but is not mutually exclusive, or at least is not the mutually exclusive concept. And today we've arrived at that concept. That concept is the concept of independence. It's a very common student mistake to mix up the two terms, independence and mutually exclusive. And they are not the same thing. And you really need to be conscious of that because it can kind of mess you up if you don't. So let's take a look over here. Mutually exclusive and independent. Independent. So we start with a definition of independence, which is probably a good place to start. Two events are independent if knowing whether or not one has occurred does not change the probability that the other will occur. So we'll go with the idea, are the events female and prefers English independent? So let's gather our data. Most of the time people will say, yeah, of course it's independent. If I know a person's female, that doesn't mean I'm going to know whether or not they prefer English. They could not, whatever it is. That's the general way of thinking. You're going to find out that that's wrong in here. So what we're going to do is we're going to collect class data and fill out this two-way table and Venn diagram. So obviously there's no class for us to get class data from. So we'll just take a look at some from a previous class of mine. So here we have 1 year's class. We have females. There were 14 in class, and 9 of them preferred English, 5 of them preferred math, for a total of 14. The males were split 10 and 6, and as a class it was 19 and 11. This was a very difficult class, I remember, because so many people were actually English people, which actually you do get a lot in stats. Just because, well, I'll let you think about that one. So let's see. Let's start filling this out. We have female and English. So how many of the people in the sample were both female and preferred English? Well, that was 9. The next one over here, well, that's going to be right over here. That's going to be they're female, but they prefer math, or they don't prefer English. So female math is 5. And then on the other side here, we have English, but not female. So not female means we're in the male side of things, and they prefer English. So how many males preferred English? And that was 10. I said earlier that none of the numbers that come from, or that are in your Venn diagram, are going to be from a marginal total. And as you can see, that kind of is true here. None of the numbers that we're putting in here come from the margins. Margin meaning the totals. So there are 6 people who are neither female nor preferring English. So that means they're male and preferring math. And that's 6. So we're going to do some review here. Let's randomly choose what's the probability of a female. Female is 14 out of 30. Not female, that's going to be 16 out of 30. English, that's going to be 19 out of 30. And then not English is going to be 11 out of 30. Now I hope that you've seen the pattern that if it's just a single event going on here, female, English, not female, not English, then we looked almost exclusively, well, in this case, we looked exclusively at the marginal totals. And so in that case, it's a lot easier to look at the two-way table than it is to look at the Venn diagram. Let's take a look at the other one. We have female and English. Female and English is what we would call a joint probability, because we're looking at one of the insides and we're dividing it by the total, the grand total really. So female and English is 9 out of 30. Okay, the next one is English and not female, which you can translate that to English and male. So that's going to be 10 out of 30. Okay, English and not female, that is 10 out of 30. The next one is female and not English. That's going to be 5 out of 30. Lastly, we have not female and not English. That's going to be male and math, and that is a total of 6 out of 30. The last one here is or. It is female or English. So this is used a general addition rule or mutually exclusive addition. So that means I'm going to use general addition rule here because I'm not sure that anything is mutually exclusive. That's the best way to start off these. So we're going to do the probability of female plus the probability of English minus the probability of female and English. That is the general addition rule. So that's 14 of 30 plus 19 of 30 minus 9 out of 30. So that's going to be, I think that's 24 out of 30. Hopefully that quick little refresher is going to be good for you. Now we're going to move on to new stuff. So this is going to be called conditional probability. And you're going to look at all of these these next two, they have a condition, given that they're male, given that they're female. So I'm going to examine a little bit more about what this means. So this question 4 says, what is the probability that a student prefers English given that they are female? So let's take a look at that chart again, a two-way table. And we're saying given that they're female. So what that means is we are only going to be looking at the row that says female. Given that they're female means look only at the female row. So if I'm only looking at the female row, what's the probability that a student prefers English? That's going to be 9 out of the 14 in the female row. So this is saying 9 females prefer English out of the 14 females in our sample. Given that they're female means that this denominator down here is actually female. Now there's a special way to write this, and that looks like probability of English and then this vertical bar and then female. Okay, so that means that we're looking for English out of all of the females. How many English people are there out of all the females? So now that we have that one, let's take a look at this next one for the males. Let's see if we can do this one. I'll color code this one blue so we don't mix it up with the females. So given that they're males, the way to correctly write that, probability that someone prefers English given that they are a male. So we can take a look at the male line now, only the male line. And we'll see how many English people do we have on the male line. And that is 10 out of the 16 males in the sample. So coming back over here, this is just going to be 10 out of 16. Now there's a whole formula that goes along with this, which we'll definitely look at once we get to our check your understanding and our important ideas. But I think it's much more, you'll get much more use out of this concept if you just think about what this means. Out of all the females, out of all the males, how many prefer which? So let's see. Are the events female and prefer English independent? Well, if I know someone's female, what's the probability that they prefer English? That's 9 out of 14. And let's compare that. If I know someone is a male, the probability that they're going to prefer English is 62%. And if I don't know if they're male or female, the probability that they prefer English is 0.633. So in other words, if I know that someone is female, there's a slightly higher probability that they prefer English. So knowing whether someone is female means that I know that the probability of the other event preferring English is different. So that means female and prefers English are not independent, which you can also describe as saying that they are dependent. So for independence, this has to hold true. The probability that a person prefers English, given that they're female, should be the same as the probability that a person prefers English given that they're a male, and that should just be equal to the probability that they prefer English. In other words, knowing if someone is male or female does not increase or decrease the odds that they prefer English. So, to take a deeper look at independence, we're going to consider the following distribution of seniors at Taft. So we have females. We got 600 seniors at Taft. That's actually a lot more than we normally have at Taft, by about threefold, maybe 2.5-fold. So we'll do some of the easy stuff here. We'll do the probability of English. That's equal to 330 out of 600, which is 55%. What about the probability of English given female? So we're only looking at the female line, and that's going to be 180 out of 320, or about 56%. So we're already saying that they're not independent. But we might as well look at the male line, which is not female. So let's look at the not female line. Well, that's going to be 150 out of 280, which is predictably not the same as 55. So what if these were independent? What would this table look like? Okay, so we're going to do 3 stripes here. Let's first figure out the probability of English. So I'm going to do probability of English. Let's do that with green. Well, that's got to be 330 out of 600, or 55%. Well, if females were independent, if the female or not female was independent, that means 55% of the females have to also prefer English. So X out of 320 has to equal 55%. With a little bit of algebra, you can see that that number has to be 176. And because we have to add up to 320, 320 minus 176, that's going to give us 144. Now, let's look at the male line, or the not female line. Just like with the female line, some number out of 280 total males has to equal 55%. With a little bit of algebra, we get the number 154. And then with a little bit of subtraction, we get that the male in math has to be 126. A couple of ways of doing that. You can have 154 plus 126 equals 280. You can even have 144 plus 126 equals 270. Those two problems should work out. And once you're at that last little bit there, all of these 4 have to add up to 600. So that's 3 different ways that you can get that 126. So what do we notice about the questions numbers 7 and 9? What do we notice? And this one might be a little bit difficult to see, but if we're talking about independence, then the probability distributions are the same for every row, and they're also the same for every column. For example, 330 out of 600 is equal to 55%. 154 out of 280 is equal to 54%. and also 176 out of 320 is equal to 55%. But it also works for the columns. So you'll notice that 176 divided by 330, that's going to be about 0.53. Also, 144 divided by 270, that's about equal to 0.53. And finally, 320 divided by 600, that's also equal to 0.53. So it doesn't matter if you're looking at a conditional probability for a row, or if you're looking at a marginal distribution, those will all be the same. So, generalize. Complete the following statement. If events A and B are independent, then, and then this is our formula, the probability of A is equal to the probability of A given B, and it's also equal to the probability of A given B complement. In fact, it doesn't matter what you put on the other side of the given that, it's always going to be the same probability. And that takes us to our big ideas for today. So we've got the conditional probability, and this formula over here, my gosh, probability of A given B is equal to the probability of A and B divided by the probability of B. It's a lot easier to think of that in terms of the row in the table or the column in the table than it is to think about it in terms of this formula. But the formula is true if we remember that the inside cells of a two-way table is and then any of the row total or the column totals is just a single event, A or B. So it does make sense in that respect. And then finally, the thing that we've been working on most here is this thing about independence, where knowing one event has or has not occurred will not affect the probability of the second event. And then at the bottom here, we have that really fun definition, mathematical definition for independence. Remember that also that you only have to check two of these if the first two are not equal. And by the first two, I mean if these two are not equal, then there's no reason you have to check the third one. That's not going to work either. Or if you check these two and it's not equal, then you don't have to bother checking this one. It's not going to work. So as long as two of them are unequal, then we have dependent events. Sounds good? Okay, let's take a look at to check your understanding. Yellowstone National Park surveyed a random sample of 1,526 winter visitors to the park. This is Yellowstone. They asked each person whether he or she owned, rented, or have never used a snowmobile. I personally have never used a snowmobile, so this is totally foreign to me. But I guess that kind of puts me in your place a little bit sometimes. Respondents were also asked whether they belong to an environmental organization such as the Sierra Club. The two-way table summarizes the survey responses. Okay, suppose we randomly select one of the respondents. Let's say E is environmental club owner member, and S is a snowmobile owner, and N is never used. Let's find a probability of N given E. Okay, let's start highlighting things. E, that's environmental club member. So that's yes, they are an environmental club member. Okay. Okay, so what's the probability of N given E? So if I'm only looking at that E column, the number of people in that E column, the environmental club member column, who have never used a snowmobile is 212. So the probability of N given E is 212 out of 305, which is about 0.6951. Interpret that value in context. And the most expedient way, probably the easiest way that makes most sense English-wise, is to say that 75% of environmental club members have never used a snowmobile. Now, you could probably use some given that language. Using that language, you would say that the probability that a respondent has never used a snowmobile, given that they are an environmental club member, is about 70%. Which reminds me that in my previous one, I really need to say that 70% of environmental club members in the survey have never used a snowmobile. Because we're only talking about people in this survey. Okay, next, given that a person is not a snowmobile owner, what's the probability that he or she is an environmental club member? Okay, so this time we're going to be saying given that they are not a snowmobile owner. So we're going to look at a not the snowmobile owner. So if they're not a snowmobile owner, then they are either never used or they are a renter. Okay, both of those categories together are not a snowmobile owner. Okay, so what's the probability that they are an environmental club member? All right. Symbolically, we would say the probability that of E given S complement. Okay, so we're only taking a look at S complements. And let's see, how many environmental club members are there in the S complement group? There are 212 and 77. 212 in the never used section and 77 in the renter class. So that is what, 289? Let's just write 212 plus 77. And we're going to divide that by the total number of not a snowmobile club people, which is these numbers over here. 657 plus 574. And that gives me 2348. So there's a probability statement using correct symbols. And I think that's all we need. We don't actually have to interpret that. Oh yeah, duh. The interpretation is actually the question. About 23% of the survey respondents are not a snowmobile owner, given that they are, are an environmental club owner, given that they are not a snowmobile owner. So now the question is, are the event's snowmobile owner and environmental club member independent? So let's remember what this means. Snowmobile owner and environmental club, are they independent? So there are so many ways that you can test this. The way that I'm going to go is if they are independent, then the probability of E is equal to the probability of E given S and the probability of E given S complement. Now you could have also used the probability of S equals S given E and equals S given E complement. Either of those two would work. But the reason I chose the first one is because I already have one of the probabilities. I already know probability of E given S complement. Okay, so all I need to do is compare that to the probability of E. So what is the probability of E? The probability that someone is an environmental club member is 305 out of 1526. 305 out of 1526. So we're going to compare those with these. And if they're equal, then we have independence. So over here we've got 305 out of 1526. That's equal to about 20%. Okay. let's copy the results from the previous work we did. And since these two numbers are not the same, then they are they're not independent. So since the probability of E is not the same as the probability of E given S complement, E and S are not independent. So that kind of does it here for independence. Again, it's a very nuanced subject, and it's really easy to get lost. It's really easy to confuse these with mutually exclusive. So you have your work cut out for you. I'll see you guys in class, and good luck with this section. See you next time.